All right, hello everybody. We are back and we're going to be still working on some radical problems here. This time we're going to be adding and subtracting some radical expressions. Okay, now one rule to go over before we go over this. Okay, so again, it can be confusing with all the letters, but just listen to me as I explain it. Okay, so if you have a radical with that is just to some index and there's some radicand in there. And if you add or subtract that with another radical, okay, but notice the radicals are the same. Okay, that's the key here. Okay, you're only going to be able to add or subtract if they are radicals with the same index, right? That n number, okay, and they have to have the same radicand. They have to have the same radicand and the same index to be able to add or subtract, okay? So notice, you do have that, if you do have the same radical with the same index, if there's numbers out in front of those, you can add or subtract those, okay? You would just be left with that added number or subtracted number with that same radical at the end, okay? So that might still be confusing. Let's just do some examples and hopefully that'll clear it up, okay? So like if you look at number one here, we have 5 times the square root of 2 minus 3 times the square root of 2. Okay, so in this case, we have a radical, right? We have the square root of 2 and then the square root of 2 in the second term as well. So it fits both of these. They have the same index, they're both square roots, and they have the same radicand, right? That 2 is in the radical. So that means we're going to be able to subtract these, and we can just do 5 of these, 5 square roots of 2, minus 3 square roots of 2 to give me 2 square roots of 2, okay? I'm able to subtract those just like that. It's kind of like with like terms, right? If I had 5x minus 3x, I would have 2x, right? It's kind of the same idea. Now, number two, you look at this, okay? This is saying 7 times the cube root of 11 plus 6 times the square root of 11. And you think, okay, can I add those together? And in this case, right, they have the same radicand, right? 11 is the number in the radical, but the indexes are different, right? This is a cube root, and this would be a square root, okay? So you cannot combine. Yeah, you can't combine those because of those different indexes, okay? Now moving along, number 3 here, we look at this one. 9x times the square root of 10 plus 2x times the square root of 6, okay? Again, we look at these, they have similar numbers outside of the radical. We could call those coefficients, right? And so the square root of 10 and the square root of 6, right? Same type of root, the same index, but different radicands, okay? Now in this case, again, we're going to see some other problems where this isn't just, you can't just assume we can't combine these, but in this case, we can't reduce these radicals, right? 10 and 6. If we were to break these down, right, 10 would be 2 times 5 and 6 would be 2 times 3. And so I can't reduce any of these radicals. So in this case, because of that, we can't reduce or can't combine. Okay, now number 5 is going to be one where we are going to have to change things, even though you might look at it at first and think, oh, different radicals, so I can't combine. That's not the final answer. That's not, you have to do a little bit of work to get to that. Okay. But first we'll do number 4 here, right? So 4 times the cube root of 15 plus 8 times the cube root of 15. Okay, so do your checks. Same index. Yes, they're both cube roots. Same radicands. Yes, both 15 under the radical. So I can add these, right? So 4 plus 8 would give me 12 times the cube root of 15. Again, so the common mistake would be to say 12 times the cube root of 30, right? Kids try to add the radicand numbers as well, but you wouldn't do that. That would stay the same. It's just kind of saying 4 of these plus 8 of these gives me 12 of these. Okay, so just adding the numbers out in front. All right, now number 10, or sorry, number 5. For this one, again, you might look at this at first and think, I can't combine. They don't have the same radicands. And that's true at first, okay? But, so just like with fractions, if you were to try to add like 1/3 plus 1/6, right? Right away, that might be a little bit hard, right? You actually couldn't add these right away because they don't have the same denominator, and that's what you would need to add these. But if you would convert this one to have the same denominator, so 2/6 plus 1/6 would give you 3/6, then you can add them. Okay, so right away they don't look like you can add, but then when you change one of them, you can. And that's what's going to end up happening here for number 5. Okay, so 10x times the square root of 3. Again, that square root of 3, that radical, I can't break that number down any further because 3 is a prime number. Okay, and square root of 12. Now the square root of 12 is that's not a perfect square, but again, what you kind of think, is there any perfect square factors? Okay, or again, what some of you might do too is that factor tree, right? So break down 12 into 2 times 6, and then break down 6 into 2 times 3, right? So you could rewrite the square root of 12 as the square root of 2 times 2 times 3, right? And again, your rule with radicals is because you have that double, that pair of 2's, that can come out of the radical. Okay, so we can rewrite this. Okay, and then look what number is left in the radical, 3. And that's what this one is, right? So I am going to be able to combine these. Okay, now let me just rewrite this. So again, that 4x was outside originally. Okay, but again, this 2 came out of the radical when I reduced it. So it's going to be 4x times 2, and then the square root of 3. Okay, and then the last thing I can do is combine these 4x times 2 to give me 8x times the square root of 3. Okay, so I rewrote this 4x times the square root of 12 as 8x times the square root of 3. And then again, now I can do the subtraction. So if I have 10x times the square root of 3 minus 8x times the square root of 3, again, same radical now. So I can subtract 10x minus 8x to give me 2x times the square root of 3. Okay? So you can combine those, but you just have to simplify or change that one radical first. Okay? So that one's a little bit trickier. I'll do another couple like that, but that's adding and subtracting, just a taste of it for now. Okay? All right, so I added a couple more problems up here that are more similar to what we saw in number 5. Okay? So again, you look at these at first and you might think, okay, none of these radicals are the same, so I'm not going to be able to really combine any of them. But again, that's not kind of the final answer. That's not the final thing you say. We have to check to see if we can reduce these. Okay, so square root of 12, I gave you that here. And so if you do that for one problem, right, we know that the square root of 12 is going to reduce to 2 times the square root of 3. Okay, so let me just rewrite that right now. So then I look at, okay, square root of 75. Okay, now you can do it with the factor tree like this. Okay, that is one way to do it. I did show you guys the other way to do it as well, right? Right, so if you think of your perfect squares, right, I only have a few of them listed here, but again, we think, okay, does this number have any perfect square factors? Okay, and 75, right, you think, okay, do any of these numbers multiply to give me 75? And yeah, 25 does. Okay, I could say, right, the square root of 25 times the square root of 3, right? Isn't that the same as 75, right? And so then I say, okay, 25, the square root of 25 is 5. Okay, so I could rewrite the square root of 75 as 5 times the square root of 3. Okay, and notice what I have. I have 2 terms now that have the same radicand and the same index. So I'm going to be able to add those. Okay, but just finish simplifying, right? So this 48, this minus 48, again, square root of 48, same question. Do any of these numbers multiply to give me 48? And in this case, yes, there's actually more than one. Okay, so 4, I could say 4 times 12 is 48. But one that's easily missed, right? If you did 4 times 12, you'd kind of reduce it part of the way, kind of like 4/8 reducing down to 2/4. Yes, it's reduced, but you can reduce it further, okay? 16 also multiplies to get 48, okay? And that's a higher perfect square. So the square root of 16 times the square root of 3, that's going to be the same as the square root of 48, okay? And then the square root of 16 is 4, right? So 4 times the square root of 3 is how I can rewrite that one, okay? So now look what I have. I have 2 times the square root of 3, wrote it a little lower so it's all even. So 2 times the square root of 3 plus 5 times the square root of 3 minus 4 times the square root of 3. So now, right at the beginning, it didn't look like we could do it. But now, because I have a common radicand, I can add and subtract these terms, right? So if I have 2 square roots of 3 plus 5 square roots of 3, I would have 7 square roots of 3, and then 7 minus 4 square roots of 3, and leaves me with 3 times the square root of 3. Okay, so that's how many of those I would have left. Okay. Now, number 7, same idea, okay? I have 3 cube roots, right? It's always good to look at the index first. So if these do have a matching radicand after I reduce, I could subtract them, right, or add them. But for this one with cubes, right, I'm thinking in terms not of perfect squares, but perfect cubes. So my perfect cubes, right, 1, 8, 27, 64, 125. Those are my first 5 perfect cubes. And so with these, right, I'm thinking, can I reduce these, right? So with 250, right, I'm thinking, do any of these numbers multiply to give me 250? And yes, okay, and again, with these bigger numbers, it might be hard to do that on the top of your head, okay? So what you could do is just say, okay, 250 divided by 8. If you get a whole number, then yes, that means it divides evenly or multiplies evenly. You could do 250 divided by 27, you'd get a decimal. 250 divided by 64, you'd get a decimal. 250 divided by 125, you would get 2 as an answer, which tells you if you go backwards, 125 times 2 equals 250, right? So yes, that is a cube, perfect cube that multiplies to get 250. And so I can reduce it. I could say the cube root of 125, which ends up being 5. So right? That's saying 5 times 5 times 5 is 125. So 5 times the cube root of 2, okay, that's what this first one reduces to. Minus, okay, so this would be saying like minus one of these, okay? But again, we think 54. 54, does that have any perfect cube factors? So again, you might not know off the top of your head, but if you check by dividing, 27. 27 times 2 is 54, right? So I can say the cube root of 27 times the cube root of 2 is equal to this, okay? And then I do, okay, cube root of 27 would be 3, okay? So 3 times the cube root of 2, okay? And again, now I'm subtracting those. So I can do that because they have matching radicands, right? So that's great. Now we check this last one as well, right? 16. Any perfect cube factors there? Yeah, 8, right? I could say cube root of 8 times the cube root of 2 equals the cube root of 16. Great. And then the cube root of 8 would be 2, right? 2 times 2 times 2 is 8. So I could say plus 2 cube roots of 2. Awesome. So they all end up matching, okay? So I can add and subtract these, right? So 5 times the cube root of 2 minus 3 times, so 5 of those minus 3 of those leaves me with 2 of those. So 2 of those plus 2 of those gives me 4. So I have 4 times the cube root of 2. Now, I just want to say one thing before I let you go. Okay, so these 3, right, they all end up matching for these problems. Okay, sometimes they don't. Sometimes you're left in a situation where you might have like 3 times the square root of 2 plus 5 times the square root of 2 minus 4 times the square root of 6 or something like that. Okay, and now just because one of them is different doesn't mean you can't add some of these, right? You can still add together the matching ones, okay? So you can say 3 square roots of 2 plus 5 square roots of 2 gives you 8 square roots of 2, but then you just can't combine this one. So your final answer would be 8 square roots of 2 minus 4 square root of 6, okay? And then that would be it, okay? So that happens sometimes. I just wanted to say that because these ones, they all ended up reducing nicely, but sometimes it doesn't, okay? So that is all. Thank you guys for following. Good job.